Hi, AP Chemistry. Welcome to part 2 of Unit 5 of Kinetics. We're going to be looking at reaction mechanisms in this video. So we finished the previous video on this slide. So we are talking about an elementary reaction. All right, these are the steps of a reaction mechanism. A reaction mechanism is proposed of multiple elementary steps, and the rate law is kind of used to come up with that. So the rate law for an elementary reaction, again, these are the steps of a mechanism, is based on the stoichiometry. So this would be first order, first order, first order, first order, second order, second order, second order, first order, based on how many reactants, and we'll see a couple examples of these. All right, so it leads us to this idea of molecularity. All right, we have unimolecular reactions where a given reactant forms a product. We have bimolecular reactions where two reactants form a product, and it could be the same reactant, so it could be two of something, right? We're writing it A plus A, but that could also be written as 2A forming products, or A plus B. And these are what the rate laws look like, right? So for our unimolecular, the rate law would be K times the concentration of A. Unimolecular, based on its stoichiometry, is first order. Bimolecular, based on their stoichiometry, it's either concentration of A times B or the concentration of A squared. But again, it's based on the stoichiometry. And there can be termolecular, right? A plus B plus C. So the rate law would be K times concentration of A times concentration of B times concentration of C. A plus A cubed, A plus B, A squared times B, right? Uni, bi, and termolecular. That's the molecularity of a reaction. When I say molecularity, I'm thinking of the molecules participating in a collision. All right, more than 3 is very uncommon. It is something that we don't even include in the AP curriculum. It's very unlikely, right? So our reaction mechanisms, they take a pretty complicated reaction and they break it down into these smaller elementary steps that are either uni, bi, or termolecular, right? And it allows for these complicated things to be broken down into simpler steps. All right, and each individual elementary step will have its own rate law. All right, now, elementary reactions involving the simultaneous collision of 3 or more particles are rare. Even the termolecular are rare, but we're not going to get that or more, right? So it's typically going to be either uni or bimolecular. All right, so we're using the collision model to explain this, right? For an elementary reaction to successfully produce products, reactants must successfully collide to initiate bond breaking and bond making, right? So the collision, it has to have sufficient energy, right? If there's not enough energy, it's not going to get the bond to break, right? And that's the energy being put in. Remember, we have to put in energy to break a bond. We release energy when a new bond forms. And the collision, it's going to have the right orientation. Ooh, I don't know what just happened there. All right, so the carbon dioxide, I don't know why I don't have a mouse anymore. Let's see if we can get this back on track. So the carbon in the carbon monoxide has to strike the oxygen. If 2 of the oxygens strike, they're just going to bounce off, right? That's not the right orientation for the collision. We want the carbon to strike the oxygen. It'll form this temporary OCOO, like all 4 atoms will be bonded for a second, and then that oxygen, it'll get kicked out. All right, so we see in example A here, they collide and there's no collision. All right, now since the orientation isn't changed, I have to suspect that in A, there is not sufficient energy, whereas in B, they collide and now we make these 2 new products. All right, so that's the collision model, and these elementary reactions are based on the collision molecule, which is why we don't get that 3 or more very often, right? Because these collisions, they have to happen in a very particular way. Now, in most reactions, only a small fraction of the collisions lead to a reaction. Successful collisions have both sufficient energy and to overcome the energy barriers and orientations that allow the bonds to rearrange, right? So we get all of these molecules bumping around in a sample. Only occasionally are we producing successful collisions. Now, let's just pause on this slide for a second to think. In the very beginning of kinetics, we talked about factors that increase the rate of reaction. So one of them was concentration. Well, if we have a higher concentration, we're going to get more collisions, right? And hopefully more of them will be successful. So this collision theory does do a nice job of explaining how we get faster chemical reactions. All right, so now the Maxwell-Boltzmann distribution, all right, and we've seen that before. This is a distribution for temperature. Here we're saying kinetic energy, right? It describes the distribution of particle energies. This distribution can be used to gain a qualitative estimate of the fraction of collisions with sufficient energy to lead to a reaction, and also how the fraction depends on temperature. So what'll happen is a distribution of molecules, because of their temperature, right, the higher temperature molecules have the higher kinetic energy. They're moving faster, right? The molecules are all at the same mass because our kinetic energy, it's 1/2 mass times velocity squared. So whatever the activation energy is for a reaction, we can plot that, and any particles past it are going to have sufficient energy. So now if we're thinking about two separate temperatures, when we get that higher temperature, the higher temperature is the flatter curve. So the higher temperature is in black in image B. And so at the same activation energy, we get more particles. All right, I know it looks weird. This would be integration for the people that are in calculus, but it's the area underneath the graph. There are more particles in the higher temperature with sufficient kinetic energy than in the lower one, right? And this is the Maxwell-Boltzmann distribution curve. So that's why higher temperature leads to more successful reactions, a faster reaction rate. All right, so now the elementary reactions, they typically involve the breaking of some bonds and the forming of new ones. So we get this temporary transition state, and some new bonds form, some bonds are broken. Remember, breaking bonds requires an input of energy, and forming bonds releases energy. All right, and the reaction coordinate is the axis along which the complex set of motions involved in rearranging reactants to form products can be plotted. All right, I call them energy profiles, reaction profiles. We've seen these, right? We know that if we always start reactants, we go to the products. If the products are higher, we know that it's an endothermic reaction. If the products are lower, we know it's exothermic. But now we can also plot multiple steps like a mechanism. All right, so the energy profile, it gives us the energy along the reaction coordinate, which typically proceeds from reactants through a transition state to products. The energy difference between the reactants and the transition state is the activation energy for the forward reaction. All right, if we were to do the reaction in reverse, it would be from the bottom products line to the transition state. But the hump, the hill that we have to overcome is our activation energy. We can see these in these diagrams. Okay, the Arrhenius equation relates the temperature dependence of the rate of an elementary reaction to the activation energy needed by molecular collisions to reach the transition state. We saw this equation in the textbook. We didn't really use it. I think it came up in like one question that we just kind of plugged in numbers. The rate constant equals A, which is some pre-exponential factor, times the natural log base E raised to the activation energy, negative activation energy divided by R, gas constant, times temperature. All right. All it's saying is if we get a higher activation energy, we're gonna typically have a lower K, right? The higher activation energy makes it harder for a reaction to take place, right? It's a bigger barrier. But as we get a higher temperature, right, that reduces it since we're dividing by temperature. So two things I want you to take from this slide. All right, we're not going to do a calculation. We're not going to plug any of this in, but qualitatively, if EA, the activation energy, if that's bigger, we're going to get a smaller K value because of the negative. And if the temperature is bigger, we're going to get a larger K value. So higher activation energy will reduce the rate constant, but a higher temperature will increase the rate constant. And that should make sense because we've said that a higher temperature makes a reaction go faster. We do know that K, the rate constant for these reactions, is temperature dependent. So as you change the temperature, it will change. All right. And again, the activation energy, if we just think of it as the hill on that graph, the higher the hill is, the longer it's going to take people to get there. The longer it's going to take a reaction to have that amount of energy for it to occur. So again, we're not going to calculate the Arrhenius equation, but it can be used to kind of explain a couple of pieces we know about reaction rates. All right, a reaction mechanism consists of a series of elementary reactions or steps that occur in sequence. The components may include reactants, intermediates, products, and catalysts. I put this picture here. If you go on Google and you search reaction mechanism, you'll get a lot of these organic mechanisms. A huge piece in being successful in organic chemistry, but they are not what we're looking at all. They can be very scary. They can be very intimidating. Some people might do them wrong for the entire semester of Organic 1 and halfway through Organic 2 and not figure out how to do them right until the very end. All right, totally not talking from personal experience there. All right, but if you do go on in chemistry, when you take organic chemistry, you really want to devote the time in the beginning to getting good at these reaction mechanisms. Ours are way simpler, right? So don't worry about all this nonsense. Way simpler. So an elementary reaction, it's one step. But a mechanism, it's multiple elementary steps, so we get multiple hills on our graphs. All right. Now the activation energy, it's still reactant to transition state. So that's a low activation energy. This is a slightly bigger activation energy. And we can see that it's two steps for this reaction. All right. So mechanisms are multiple steps, and we should keep the word step synonymous with elementary reaction. All right. So two steps. We have this big first step, right? We make our intermediate, and then we have a second transition state. We make the products, right? So the intermediates, they do not make it all the way to the products. If we have the elementary steps written out, the elementary steps, when combined, should align with the overall balanced equation of a chemical reaction. All right. So what we end up seeing is the NO2s, the excess NO2s get canceled out. The NO3 is an intermediate that gets crossed out, right? And in the end, our reaction is NO2 plus CO yielding NO plus CO2, all right? So this is the reaction we're looking at. This is the proposed mechanism. It is two steps. And again, NO3 is an intermediate. And it's totally fine that we have two NOs in the beginning because one will get canceled out later. So it gives us the overall reaction. All right. So again, a reaction intermediate is produced by some elementary steps and consumed by others such that it is present only while a reaction is occurring. What that is saying is the intermediate never makes it to the end. We have our overall reaction here. The intermediate is being produced in step one. The intermediate is ClO, and then it's being consumed in the second step. All right, so what does that make the Cl? Because the Cl starts in the reaction, it's made by the end, and it's not in the overall reaction, so the Cl is actually the catalyst. All right, now, experimental detection of a reaction intermediate is a common way to build evidence in support of one reaction mechanism over an alternate mechanism. So we do try to set up these experiments to figure out, to see if we can observe the presence of the intermediate. This is from a big experiment that happened back in the winter, where they were using ultra cold chemistry to slow down the reaction to the point to try to observe the intermediate, which was gone in the blip of a second anyway, but they were able to get some data to identify that intermediate. All right, and again, it's just something that it's there temporarily, but then it's gone. It's not there at the end. All right, so for reaction mechanisms in which each elementary step is irreversible, or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step. So we call this the rate limiting step, also called the rate determining step, RTS, you'll see. So we get information. The first step is slow, the second step is fast. So the rate is based on the slowest step. We don't care about those faster steps, right? Because our reaction's only as quick as our slowest step. Think about like the team's only as good as their weakest player. So in step one, the rate would be concentration of NO2 squared, because it's bimolecular, all right? And we wouldn't even worry about anything happening in step two, and that would explain the rate for this overall reaction, right? Step one is the rate determining step. And we often see this information given, slow, fast. All right, so a classic example is if we were to use a series of funnels and one of the funnels was really small, right? We only move as quickly as that slowest funnel allows us. All right, here's another example. All right, but in this example, we have to make an approximation. All right, so if the first elementary reaction is not rate limiting, right? It's easy when the first step is the rate determining step. It gets a little trickier when it's later on in the mechanism, right? Is not rate limiting. Approximations such as a steady state must be made to determine a rate law expression. All right. So something occurs as well when we get these equilibriums. So what we're seeing here is that in step one, the NO plus the O2 are in equilibrium with NO3. We are told it is fast and it is reversible. Now in step two, the NO3 plus the NO forms the 2NO2, and that's the slow step. So we want to think that step two is the rate determining step, and we're not wrong there. That is correct. But how do we determine the rate constant for it? All right, the rate constant is the concentration of NO3 times the concentration of NO. All right, now NO3 isn't even in the overall reaction. There can, it's not impossible. An intermediate can be in the rate constant, but it's very rare. Now, what we want to do is we want to make this approximation. So what we're going to look at, and it's all explained down here, and I think they overcomplicate it for us. The NO3 intermediate, it's in equilibrium with the NO plus the O2. So we can totally substitute them. What they're doing down here, if you pause on this slide, they're saying that the forward reaction has a rate constant of concentration of NO times O2. And since it's reversible, the reverse reaction is the concentration of NO3. And so they are putting both in, and they're doing forward over reverse, right, to substitute in. So the overall rate, it's K2, the second reaction, times the forward over the reverse. So the NO3s cancel out. And so we're left with 2 NOs and 1 oxygen. Well, I would say, right, because we're given the rates here, I would say anytime you have an equilibrium, whatever the product of that equilibrium is, when we see it in a later step, we can substitute the reactants for that product in a later step. All right, so since we see the NO3 here, and it is an intermediate, and it's in an equilibrium in the previous step, we can just substitute the NO plus the O2 as if they were here. So that's why we would get the rate constant of NO squared times O2. I know that's really complicating things, but for the equilibrium, again, you can just substitute. That's the easiest way to think about it. All right, so here is a nice example that we can look at. All right, we have 2NO forming N2O2. It's a fast equilibrium, step one. Step two, N2O2 plus H2 forming H2O plus N2O. This is a slow step. And then step three, N2O plus H2 forming H2O plus N2. This is a fast step. So our slow step is the rate determining step. So it's going to be the concentration of N2O2 times the concentration of H2, because this is bimolecular. But N2O2 we can substitute as 2 NOs, so that would actually make it termolecular. So the rate is going to be concentration of H2 times the concentration of NO squared. All right, and they're going to go through all this math with setting up K1 and K inverse 1. You don't have to do that. You can just substitute. You're going to get NO squared over H2, right? And the K will solve for in a different manner anyway, so you don't have to worry about that. All right, now knowledge of the energetics of each elementary reaction in a mechanism allows for the construction of an energy profile for a multi-step reaction, right? So we can put the reactants, the first transition state, the second transition state, the intermediates, and the height of these states. The rate determining step will always have the largest activation energy. So if I'm looking at this graph, right, the activation energy for the first step, it's from A to K. It's that distance, not that high. The activation energy for the second step is from J to D. All right, so it's not from the initial reactants, it's from where the intermediates start, but it's a much higher distance. So I know that the rate determining step is the second step in this mechanism based on its profile. All right, so again, the faster steps have the lower activation energies, the slower steps have the higher activation energies. So it's something that it's detail that we can put into one of these reaction coordinates if we had to draw one ourselves based on given information. All right, now in order for a catalyst to increase the rate of a reaction, the addition of the catalyst must increase either the number of effective collisions and or provide a reaction path with a lower activation energy relative to the original reaction coordinate. So typically we can say that a catalyst speeds up a reaction. Yes, that's true. We can say that a catalyst lowers the activation energy. Yes, that's true, but what it's really doing, it's providing an alternate pathway, right? Now the alternate pathway may have multiple steps, but it definitely has lower activation energy, so we will reach the products quicker with that catalyst present. All right. The catalyst is always something, it doesn't have to be in the very first step of a reaction, but it's something that will be consumed in the reaction, but then regenerated by the end. So in a reaction mechanism containing a catalyst, the net concentration of the catalyst is constant. However, the catalyst will frequently be consumed in the rate determining step of the reaction, only to be regenerated in a subsequent step in the mechanism. All right, you don't need a lot of catalyst because it'll keep regenerating itself. All right, so intermediates are things that aren't in the overall equation. So C and CD are intermediates, but D is the catalyst because it's being regenerated by the end. Yes, we cross it out. It's not in the overall equation, but it's there at the end of the reaction. So it's available in like the next round of the reaction. All right, now some catalysts accelerate a reaction by binding to the reactants. The reactants are either oriented more favorably or react with lower activation energy. This is often a new reaction intermediate in which the catalyst is bound to the reactants. Many enzymes function in this manner. All right, if you remember from your biology classes, kind of like that lock and key model, but the enzymes, right, they allow for two substrates to come together while connected to the enzyme, and they leave. The enzyme is regenerated, so it's our catalyst. All right. In surface catalysis, a reactant or intermediate binds to or forms a covalent bond with the surface. This introduces elementary reactions involving these new bound reaction intermediates. All right. This is an example of a palladium catalyst. In your cars, your catalytic converter is another catalyst. It's a metal. These are often metals where the atoms bond to the surface of the metal, and then they can bond with each other on the metal to form the new products, and then they leave. All right, so oftentimes these catalysts occur as a metal, and that's really all there is to say about the catalyst. So those are just kind of the examples of them, but not things that we use all that often. All right, so I know it's kind of a quick one, but this concludes Unit 5. All right, you may want to do a little bit of practice with some of the different types, and I'll try to put together some questions to look at. Big things to remember. The graph of concentration versus time, that's how you can determine the rate order. So you want to look for those linear expressions. Knowing the units of the rate constant K. All right, so you have to kind of think about what the order of reaction is, and the units for the K can change. If K is very high, that means the reaction is occurring quickly. If K is really small, the reaction is occurring slowly. And being able to interpret those reaction profiles. All right, we know that we go from reactant to product. We can have intermediates along the way. The activation energy is from the current reactant, and we can view that as like an intermediate, but from wherever we are on it to the peak of the transition state, rate determining steps will always have the highest activation energy. All right, so that should be a nice review of Unit 5, Chemical Kinetics. Our next review will be Unit 7, Equilibrium.